Testing. Testing. Testing, testing, testing. Testing, testing, testing. Testing, testing, testing. Testing. Testing, testing. Hello? Hello? How are we doing? Why is this not working? Audio not working? Hello? Okay. Audio is working. All right. Happy Monday. Hope you had a good weekend. Today we're going to start off with a paper. This is a paper. The source of this paper is, again, this Hugging Face papers page. I'm kind of loving this. It's kind of replacing papers with code for me. But yeah, it seems like it had a lot of interest, and it's right up our alley. It feels like I've been on a kind of a theme here of variants of image generation models, and this one seemed too interesting to pass up. So this paper is called HyperDreamBooth. Hyper networks for fast personalization of text-to-image models. Text-to-image models are just generative image models, right? Go from a text to an image. So Stable Diffusion, Midjourney, all of your favorite generative AI products. This is coming out of Google Research, 13th of July, so relatively recent here. And let's look at this picture here. Using only a single input image, so I guess that's what this picture is here. I bet you this is probably one of these researchers. That's probably what it looks like. HyperDreamBooth is able to personalize a text-to-image diffusion model. So this text-to-image diffusion model here is probably image gen, given that this is a Google paper, but I'm sure the technique they describe is general enough that you could apply this to Stable Diffusion if you wanted. It's 25 times faster than DreamBooth. DreamBooth is not known for being necessarily faster, so this isn't as much of a flex as they think it is. By using a hypernetwork to generate an initial prediction of a subset of network weights that are refined using a fast fine-tuning for high fidelity to subject detail. So some kind of fine-tuning strategy is basically what they're going to be presenting in this paper. Our method also conserves model integrity and style diversity while closely approximating the subject's essence and details. Okay, so model integrity and style diversity, there's not really a formal definition there. I think kind of what they're talking about is this catastrophic forgetting problem that you run into in fine-tuning, where if you push too many gradients, you can kind of start to lose some of the power of the original text-to-image diffusion model. And we see here, there's this new module here, HyperNetwork. So they're probably going to be training a separate module, perhaps like a LoRa, perhaps like a ControlNet. We don't know yet. And then they have their text-to-image model. And here is their text that is coming in. This V represents a special token. When you're fine-tuning these diffusion models for specific specific faces, right? Generally what you do is you basically fine-tune it with a bunch of examples of your own face, and then you make a token that represents your face, and then the text-image diffusion model learns to associate that token, which represents your name, with your face, and then that means you can now basically generate any image, and you put in that token, which now represents your face, and voila, you have your face. It seems pretty good, but these are all like kind of similar. You notice how pretty much every single one of these images is like a frontal shot where the face is roughly 90% of the image, and it's very object-centric. So I wonder how good this performs if you have a more weird kind of setup, or scene composition. Like if you had a crowd of 3 people standing at the bottom, what would happen there, Okay, let's look at this abstract. Personalization has emerged as a prominent aspect within the field of generative AI, enabling the synthesis of individuals in diverse contexts and styles while retaining high fidelity to their identities. So if you want to be making products with text-to-image models, obviously the best products you can make is give people the ability to take their own likeness and then reproduce it in diverse contexts and styles. However, the process of personalization represents inherent challenges in terms of time and memory requirements. Boo. Come here. She hears me talking on the stream, and she's like, what's going on over here in this room? You got anything to say? Okay, we're going to put you back down. Fine-tuning each personalized model needs considerable GPU time investment. I think that's really only if you're fine-tuning in the classic sense of actually pushing gradients into the text-to-image diffusion model, but I think at this point, most of the fine-tuning strategies involve different tricks that prevent you from, or that mean that you don't have to do that, right? LoRa, when you're doing a LoRa fine-tuning or OFT fine-tuning, you're fine-tuning these little extra pieces, usually zero initialized, and you're not actually pushing gradients into the full model, which means you don't need to be, you don't need a huge GPU requirement. Storing a personalized model per subject can be demanding in terms of storage capacity. To overcome these challenges, we propose HyperDreamBooth, a hypernetwork capable of efficiently generating a small set of personalized weights from a single image of a person. I don't really know exactly what they mean by hypernetwork here. I think there's probably a more archaic definition for this, but I think they're going to kind of redefine that term, if I had to guess. By composing these weights into the diffusion model, okay, so this makes me think that they're doing a LoRa, right? Coupled with fast fine-tuning, HyperDreamBooth can generate a person's face in various contexts and styles with the high subject details while also preserving the model's crucial knowledge of diverse styles and semantic modification. Our method achieves personalization in faces in roughly 20 seconds, 25 times faster than DreamBooth, and 125 times faster than textual inversion. Using as few as one reference image with the same quality and style diversity as DreamBooth, our method yields a model that is 1,000 times smaller than a normal DreamBooth model. So this is not the full model, right? The 1,000 times smaller is just going to be this extra little hyper network module here. It's not going to be the text-to-image diffusion model. That's still going to be the same exact size. But 10,000 times smaller is definitely quite impressive. And preprint under review, that just means that they published this paper, but it's not even part of a conference yet, which just lets you know kind of the state of machine learning research at this point, where you're reading the papers before they're even in conferences, right? And then by the time it actually gets published to the conference, the world has moved on. And kind of a side effect of that is that conferences are less and less important, right? It used to be the case that you kind of didn't read the paper until it was published in a conference, but now you're reading the papers and the conference is kind of just 6 months behind the actual bleeding edge. So I think that's a good thing. I think conferences and journals are kind of corrupt, and they're just there to get money and kind of promote this academic system of promotions and citations, and it's not great. You know, I prefer a world where people just publish their research on the internet and then people read it, and then that's it. You don't need to be paying some weird academic journal and then paying for a bunch of plane tickets to go somewhere and talk to people. I think the internet has shown that you can just do that all online. All right, my rant is over. We're going to dive into the introduction here. Recent work on text-to-image personalization, T2I, has opened the door for a new class of creative applications. Face personalization. The impressive diversity of these styles is owed to the strong prior of pre-trained diffusion models. So you don't want to mess with the diffusion model, right? This pre-trained diffusion model has seen so many images from all over the internet that you have to be careful when you fine-tune it, because if you push too many gradients on it, it'll become more brittle and more narrow, right? You want it to keep that diversity, that strong prior, where the prior is the data set of the entire internet. One of the key properties of works such as DreamBooth is the ability to implant a new subject into the model without damaging the model prior. Damaging the model prior, that's an interesting way of putting it. Another key feature of this type of method is that the subject's essence and details are conserved even when applying vastly different styles. Yeah, I agree, but I think that they could have been a little bit more bold with these examples. I still think that the nature of this image is kind of very, very similar to that. You know, they're, like I said, it's basically just the same ratio of a face to the rest of the image. When training on photographs of a person's face, able to generate new images of that person where a part of that person's essence is preserved and the animated cartoon figure. Hello, bro. Naughty G8YTH. How's it going? There are two core characteristics that we would like to leave untouched. Has some shortcomings, size and speed. For size, the original DreamBooth paper fine-tunes all the weights of the unit and text encoder of the diffusion model. This is the problem, right? Because when you're fine-tuning all of the weights, the amount of GPU memory you need for that is huge, because every single weight that you change in a neural net, right, with a gradient, you have to basically keep track of what is known as the optimizer state, right? And what is the optimizer state? Well, when you're doing backpropagation, you're basically very slightly adjusting every single weight based on a gradient, and a gradient which is part of a optimizer such as the atom optimizer, which also has additional terms such as momentum terms, right? And even just loading all of these weights into your GPU takes a bunch of memory. So the kind of fine-tuning where you're pushing gradients all the way through every single module in your every single neural net, that type of fine-tuning is going away for sure, which amount to more than 1 gigabyte for stable diffusion. That's kind of weird. Why are they mentioning stable diffusion here? In terms of speed, notwithstanding inference speed issues of diffusion models, training a DreamBooth model takes about 5 minutes for stable diffusion. This limits the potential impact for the work. What will you do today? I love web. We are going to be reading HyperDreamBooth, which is a paper out of Google Research, similar to some of the other papers we've been reading, but it's basically a fine-tuning strategy for text-to-image diffusion models. These AI papers are getting crazy every week. Yeah, it's definitely the speed of research is very pleasing. You know, it's great. We're kind of in a golden age right now in terms of people publishing research. Unfortunately, I don't know if this golden age will last, because I think the amount of secrecy at the big tech companies means that over time we can expect less and less published work and less papers. So I don't know. I think we got like a year or two of great papers coming out every single week, but I think eventually we're going to get to a point where they just keep it all secret, and that'll be sad. I don't know what I'm going to do. All right, in terms of speed, notwithstanding inference speed issues of diffusion models. So why do diffusion models have inference speed issues? Diffusion models have inference speed issues because they have to iteratively remove noise over a series of steps, right? Diffusion model. Everybody loves, what's my favorite diffusion model picture? I love this picture. So open image in new tab. There we go. You see, diffusion models don't work in one shot, right? A generative adversarial network, GANs, which are kind of an older technique at this point, but they're making a comeback in some ways. GANs just generate an image in one step from noise, but diffusion models remove noise over a series of steps, and every single one of these steps is a model inference. So that's why diffusion models just inherently have a inference speed issue. Training a DreamBooth model takes about 5 minutes for stable diffusion. I doubt this. I feel like that's kind of glossing over the fact that in order to even train a DreamBooth model, you need a huge-ass GPU. This limits the potential impact of the work. We want to address these shortcomings without altering the impressive key properties of DreamBooth, namely style diversity and subject fidelity. Specifically, we want to conserve model integrity and closely approximate subject essence in a fast manner with a small model. So none of these terms are quantitative things. Style diversity, subject fidelity, model integrity, and subject essence, those are all subjective things. So I don't think there's going to be a comparison here with specific quantitative numbers here, other than for the inference speed and the size. In terms of the actual quality, it's just going to be subjective. which is fine. Our work proposes the problems in size, speed, while preserving the model integrity, editability, and subject fidelity. I am more scared of law to AI thingy that's going to restrict AI research, especially open source community. Yeah, Erlen, that's definitely true. Probably the way that they're going to do that is they're going to claim that AI models are unsafe, and in order to ensure the safety, you basically need to go through a regulatory approval process to release anything. And that regulatory approval process will be particularly heavy and expensive so that only the most well-funded and big companies can afford it. And that's the same playbook that pharmaceutical companies use, right? So pharmaceutical companies, they made sure to have a very long and intense process to releasing new pharmaceutical products, and that long and intense process is so expensive and so long that it's very difficult for anybody who doesn't have a ton of money to do it. So that acts as a way of gatekeeping medical products. And I think the same strategy, the same playbook is going to be used in AI, where basically you already see step one. So step one is convince the regulatory agencies and the governments that AI is unsafe, and then propose a way of ensuring the safety, which is going to be very long and intense, and it's going to require all these different tests and checks. And then step three, enforce those. So we're already seeing step one, which is convince people that it's dangerous. So yeah, fuck Sam Altman, dude. That guy sells out humanity for his own profit. This will just slow down, yeah. It's bad for the world, but it's good for rich people, because the rich people get to be richer. Our work proposes and tackles the problems of size and speed. We propose the following contributions. So I like this. So to me, in a paper like this, you should have I like that they start with the image. I think that every good paper at the very first thing should just be a big picture like this, a big figure that lets me understand what your paper is. They have the github.io link, which I also like. I like these kind of pages. And then you have your introduction, and in your introduction, you have a bulleted list of all the things you're going to do in this paper that are unique and novel. And here we go. So already, just within whatever this is, 10 minutes of reading, I know what this paper is about and what they're going to contribute. So very well done paper so far. Lightweight DreamBooth, LIDB, a personalized text-to-image model where the customized part is roughly 100 kilobytes of size. So I think this is going to be like a little LoRa. I think this little purple thing that says HyperNetwork here, based on a couple different hints that they've dropped here, it seems like it's probably going to be like a kind of like a low-rank adaptation matrix, which is one of the more popular ways of tuning these diffusion models. This is achieved by training a DreamBooth model in a low-dimensional weight space. Yup, that's exactly LoRa. Generated by random orthogonal incomplete basis. Okay, this is a fucking mouthful here. So what is a basis? Is a set of vectors that usually are orthogonal and can be used to represent everything else in that field. Let me see if I can get a picture of this. Basis vectors. Yeah, so how about this? This is a good one. So if you have this vector here, right, this random three-dimensional vector here, three basis vectors for this are these three vectors here. And notice how all three of these vectors are orthogonal. So orthogonal basis vectors for this vector, right? But it's not limited to 3 dimensions, and it's not limited to like this kind of space. You could do it basically with any matrix. Any matrix, you could think of it as vectors in some higher dimensional space, and there is potentially some sort of basis vectors to that, right? And this kind of feeds into the whole kind of low rank world where you're trying to find simpler, ultimately ways of compressing a bunch of vectors and data and matrices into something that is very, very similar, but you can represent it with less numbers, right? At the end of the day, all of this low rank basis vectors, it's all about just taking the same thing that you have and then just being able to represent that in less numbers, Incomplete here perhaps means that you cannot represent everything with this set of orthogonal basis vectors inside of a low rank adaptation weight space. So this is the original LoRa. So it kind of just sounds like they're doing LoRa, but it sounds like they're doing some extra little tricks to it. So we'll see what those are. New hypernetwork architecture that leverages the lightweight DreamBooth configuration and generates a customized part for the weights of a given subject in a text-to-image diffusion model. Customized part. Then provide a strong directional initialization that allows us to further fine-tune the model in order to achieve strong subject fidelity within a few iterations. Strong directional initialization. So maybe it sounds like they're kind of training a more generic kind of LoRa thing, and then they're fine-tuning the LoRa? Maybe there's two. So maybe they train this hypernetwork on a big data set, and then they fine-tune it on the specific subject data set. So it sounds like there's kind of two parts here. Sounds like there's this LIDB and then this hypernetwork. All right, let's keep going. The plot thickens. We propose the technique of rank-relaxed fine-tuning, where the rank of a LoRa DreamBooth model is relaxed during optimization in order to achieve a higher subject fidelity, allowing us to initialize the personalized model with an initial approximation using hypernetwork. Okay, yeah, so it basically sounds like they're doing a two-part process. They're probably going to be training a generic LoRa, which they're calling the hypernetwork, and then they're going to basically fine-tune that in some kind of special sauced rank-relaxed fine-tuning that is specific to the subject. So maybe it's like a two-part LoRa is kind of what I'm getting from this. But we'll get it. As we dig deeper into the paper, we'll understand more and more. One key aspect that leads us to investigate a hypernetwork approach is the realization that in order to be able to synthesize specific subjects with high fidelity, we have to modify its output domain and insert knowledge about the subject into the model by modifying the network weights. I guess. Isn't you could think as everything modifying the network weights, right? So low rank adaptation matrices, LoRa fine-tuning, is about training basically a little extra set of weights, but you then take those weights and then apply them to your already existing weights. So you modify the network weights a little bit. One way that I like to think about it is that you're storing a little bit of training in a bottle, right? But modifying the output domain, pretty much everything modifies the output domain. Conditioning on text is modifying the output domain. Related work. Text-to-image models. Several recent models such as ImageGen, DALL-E 2, Stable Diffusion, Muse, Party demonstrate excellent image generation capabilities given a text prompt. Some text-to-image models such as Stable Diffusion and Muse allow conditioning the generation with a given image via an encoder network. This is the text encoder. So most text-to-image models are taking your text, they're encoding it, and then using that to condition the generation of the image. And it's not actually, you're not actually conditioning the generation. What you're conditioning is the removal of the noise by a unit, right? The way that these diffusion models are generally made, they are using a unit. Diffusion model unit. And it's the unit that's getting, here we go. Open link and new tab. Wow, this is kind of cool. I found an even better image of diffusion models. So you see here, where are we? You have your text conditioning. You can condition on anything, as they're showing here. You can condition on maps, images, whatever you want, categories, but pretty much all of these are conditioning on text. That text is going through a text encoder, and that encoded text is being used to basically condition this denoising unit, which is removing noise over time conditioned on that text, and that's why you get whatever image you want kind of appears out of the noise. Okay, techniques such as ControlNet propose ways to incorporate new input conditioning such as depth. Test, text, and image-based conditioning in these models do not capture sufficient subject details. The fuck is test text? Given the relatively small size of Stable Diffusion for the ease of experimentation, triggered. I mean, I don't know about Stable Diffusion being small. I mean, I can only load it on one of my GPUs, so to me, it's too big. We demonstrate our HyperDreamBooth on Stable Diffusion model, but the proposed technique is generic and can be applicable to any text-image model. Yeah, all of these different image gen, Stable Diffusion, these are also similar that any of these papers that work with one generally work with the other. Given one or few subject images, the aim of personalized generation is to generate images of that particular subject in various contexts. Earlier works in this space use GANs to edit a subject image into new contexts. I think they're talking about style transfer here, but style transfer with GANs is a really old technique. Pivotal tuning proposes to fine-tune a GAN with an inverted latent code. So this has got to be ancient at this point. 2022, pivotal tuning for latent. People still working on GANs, apparently. This work proposes to fine-tune a style GAN using around 100 face images to obtain a personalized generative prior. Casanova proposes to condition a GAN using an input image to generate variations of that input image. All these GAN-based techniques suffer from either poor subject fidelity or a lack of context diversity. Yeah. So far, diffusion models are winning the GAN versus diffusion war. Hypernetworks were introduced as an idea of using an auxiliary neural network to predict network weights in order to change the functioning of a specific neural network. So I guess hypernetwork is a network that predicts neural network weights. So a network that generates networks. Since then, they have been used for tasks in image generation that are close to personalization, such as inversion for style GAN, similar to work that seeks to invert a latent code of an image in order to edit that image in the GAN latent space. Okay. Personalization. Actually, wait, let's look at this image here. HyperDreamBooth training and fast fine-tuning. Phase 1. Okay, so it does look like we have two different phases here. Training a hypernetwork to predict network weights from a face image. So you have a hypernetwork here. The little unlocked here means that you're pushing gradients into it. This hypernetwork is taking a bunch of images here. It's producing these latents or these embeddings here. What are these? Oh no, it's not producing latents or embeddings. What it's producing is weights, right? It's a hypernetwork is a neural network that predicts weights. So what you have here is a bunch of weights, which I bet you are the LoRa matrices. Ground truth weights. So some kind of regularization happening here that prevents these weights that are generated by the hypernetwork from being too different from these ground truth weights. And these are used to probably condition the text-to-image diffusion model, or if they're more like a LoRa, they're used to basically modify the weights of this text-to-image diffusion model. The lock here means that there's no gradients going into the text-to-image diffusion model. It is frozen. Obviously, the text-to-image diffusion model is starting from basically a bunch of noise, and then it removes the noise from pure noise. And AV face is the text that corresponds to the fine-tuning data set here of a specific person's face, and you're trying to get this diffusion model to associate this token V with this person's face here. And it'll generate those images, and I guess you basically saying, okay, these images here should basically be the same as these images here, right? The reconstruction of this noise with this text should be this exact image, and that's what this reconstruction loss is doing. So that loss is going in between here, and this reconstruction loss and this weight regularization loss are both getting pushed into this hypernetwork here. So that's step 1. This is large scale, which I bet you means they have a ton of these, a lot of diverse data is going to be phase 1, and then you're going to end up with a hypernetwork that is more general and isn't fit to a specific domain. So it's probably a bunch of different faces. And then the phase 2, here's where you're going to put your specific face. So now the hypernetwork is frozen. You see that? Little frozen, little lock there means that it's frozen. The text image diffusion model is still frozen. You're still taking pure noise and giving it to the text image diffusion model. You still have a text that's getting encoded with a special token that represents this person. And now, okay, all right. So I'm understanding this. So basically, there's two parts to this. You have a hypernetwork, and then you have this lightweight dream booth. So your hypernetwork is basically generating a LoRa, right? It's a network that takes in an image and outputs a LoRa. And in step 1, you're just basically using a bunch of data to train the best possible hypernetwork that's as general as possible, that generates LoRa's that are very good at recreating these particular images. Then in step 2, it seems like you're going to be pushing gradients specifically into this LoRa. So you're no longer going to be pushing gradients into the hypernetwork. You're going to keep that frozen, and you're going to push a couple gradient steps into this LoRa. And then that'll give you a hypernetwork that is, or a little low-rank adaptation matrix here that is specific to your face or your concept that you want to introduce into the diffusion model. That's kind of cool. Training a hypernetwork to predict network weights from a face image such that a text-to-image diffusion network outputs the person's face from the sentence AV face if the predicted weights are applied to it. We use a pre-computed personalized weights for supervision using an L2 loss as well as the vanilla diffusion reconstruction loss. So pre-computed personalized weights for supervision using an L2 loss. I think that's this part here. L2 loss basically just means you're taking what you want and what you have and subtracting them and then squaring that, right? L1 loss is just the difference between two things. L2 loss is the difference between two things squared. Phase 2, given a face image, our hypernetwork predicts an initial guess for the network weights, which are then fine-tuned using the reconstruction loss to enhance fidelity. This is pretty badass. So you're using a network to predict the weights of a little LoRa, and then fine-tune that LoRa. So this is very different from something like ControlNet, right? In a ControlNet, you're initializing a new network from zero and then training that. But here, you're training a more generic network to give you that initial starting point for weights and then fine-tune those a little bit. Which is crazy. We got neural networks generating neural networks. T2I personalization via fine-tuning. More recently, several works proposed techniques for personalizing T2I models, resulting in higher subject fidelity and versatile text-based recontextualization of a given subject. Textual inversion proposes to optimize an input text embedding on the few subject images and use that optimized text embedding to generate subject images. So text inversion is different from any of these other techniques. In these other techniques, you're basically trying to associate specific images with a concept or a token that's going through your text embedding model, right? But textual inversion is almost like going backwards. You're basically saying, okay, well, what text embedding is best representative of my images, and then, okay, now that I know what that best text embedding is, then feed it into the diffusion model. So textual inversion is almost more like taking an image of yourself and then converting it into the semantic text space, usually of something like a clip model, and the clip model, rather than knowing exactly, like saying, okay, this is you and this is your token that represents you, it's basically taking you and breaking you down into, like, I don't know, age range and like details about your face, and then using those details about your face and feeding that into the diffusion model. 30 proposes a richer textual inversion space capturing more details. DreamBooth proposes to optimize the entire TTI network weights to adapt to a given subject, resulting in a higher subject fidelity. Several works propose ways to optimize compact weight spaces instead of the entire network, as in DreamBooth. This is IMO the truth, IMO the best way to do this. Custom diffusion proposes to not only optimize cross-attention layers, SVDiff proposes to optimize single values of a weights, and LoRa proposes to optimize low-rank approximation of weight residuals. Right, so LoRa is getting weight residuals, which you can think of it as like a delta weight. It's like basically a change to your weight. So you can store it, you can save it, and then you can apply it to your model to perform inference. Style Drop proposes to use adapter tuning and fine-tunes a small set of adapter weights for style personalization. Dream Artist proposes one-shot personalization techniques by employing a positive-negative prompt tuning strategy. Most of these fine-tuning techniques, despite generating high-quality subject-driven generations, are slow and can take several minutes for each subject. Take another sip of caffeine here. Several concurrent works propose ways for faster personalization of T2I models. The works of 12 and 31 propose to learn encoders that predict initial text embeddings, following by complete network fine-tuning for better subject fidelity. And another big problem with complete network fine-tuning, right, not only does it take a bunch of GPU memory and it's particularly expensive in terms of memory and compute, but it's also, when it comes to privacy, it's also an issue, right? I think a world where you have a frozen text-to-image model, and then everybody has little LoRa's that they can basically either keep secret or train locally, I think that's much better in terms of privacy than having a full fine-tuned stable diffusion model specifically for your face, right? It's better to have a generic big pre-trained model, and then everybody has their own little tiny LoRa that they can keep secret on their own computer, even train in secret on their own computer. And in that way, kind of the part of the model that represents you is a tiny little private LoRa rather than a full modified diffusion model. So I feel like the complete network fine-tuning is just dead for a million different reasons. In contrast, our hypernetwork directly predicts low-rank network residuals. Yeah, this is the crazy part, is that their hypernetwork, they have two networks here. They still have a LoRa, right, this low-rank network weight residual, but their hypernetwork is predicting the LoRa. So they literally have a model that predicts LoRa's. The output of this hypernetwork is a fucking model, is a LoRa. Like, that's next level. Okay, SUT. What is this? The fuck is SUT? Subject-driven text-image generation via apprenticeship learning. So maybe some kind of model distillation kind of technique here. Boo, you can't just yell all the time. My cat is upset. It then uses this dataset to train a separate network to perform personalized image generation in a feed-forward manner. Despite mitigating the need for fine-tuning, the inference model in SUT does not conserve the original T2I model's integrity and suffers from a lack of high subject fidelity. You got instant booth and taming encoder. Create a new conditioning branch, which can also be conditioned using a small set of images. Okay, so it seems like instant booth and taming encoder, what they're doing is they're basically figuring out a way to put in the representation of yourself in this conditioning. So in addition to conditioning on text, you would basically condition on some vector, some token, some embedding that represents you. Blah, blah, blah. These methods are trained on large data sets of images. Fast Composer proposes to use image encoder to predict subject-specific embeddings and focus on the problem of identity blending in multi-subject generation. The work of 5 proposes to guide the diffusion model using a face recognition loss to generate specific subject images. Usually difficult to balance diversity and recontextualizations of the subject fidelity. Face 0, celeb basis, PCA basis. PCA, principal component analysis, also very similar to orthogonal basis vectors. That's kind of in the family of that, right? You could think of orthogonal basis vectors as what comes out of principal component analysis. Okay, so that's a bunch of other different ways of personalizing text-to-image diffusion models. Generally, these related work sections are kind of a waste of time, IMO, because basically you're just learning. It's just a citation orgy, where they just sit around and they just like cite 50 different papers that are usually papers that they've worked on just to get their citation numbers up. But the part of the reason why I think they're worthless is because it's like techniques that are old. It's just a bunch of other people, other ways of doing things, but those other ways of doing things, obviously they're not going to be modern. So if you like go and you start reading some of these papers, they might already be outdated. So sometimes skipping the related work section is actually definitely worth doing if you're trying to read a paper in a limited amount of time. Preliminaries you can also generally skip if you're familiar with the type of research, but let's go ahead and read these. This is going to be their kind of introducing you to what a latent diffusion model is, what DreamBooth is, what low rank adaptation is. And generally I like reading this just because it summarizes things, right? I feel like my brain is a leaky bucket, and rereading these preliminaries every time makes sure that I really truly understand what LoRa and latent diffusion models are. Okay, so a text-to-image diffusion model, D epsilon C. C is your conditioning. D is the model. Theta here is the weights of the model. So a model is a function, right? A neural net is a function approximator. It approximates some unknown function, and that function is parameterized, right, by a bunch of parameters, theta, which are the model weights. So that's what this means. Iteratively denoises, so it removes a bunch of noise iteratively, a bunch of iterations, given a noise map, E in R H by W. So H by W here is the height and width of an image. R just means real numbers, so negative infinity to infinity. And then E is the noise map here, which you can see is actually part of what is being fed into these diffusion model function here. You have your green is the color that I use for math definitions. You have your image I. Oh my God. You have your image I, which is usually your 3-channel image, following the description of a text prompt T. So image I and text prompt T are the kind of raw form of the image in the text, but usually both of those are going to be encoded, right? So you have your input text embedding, which basically means your text prompt, but encoded with some model here. I think this is capital Phi? Capital Phi? No. Capital Theta? Yeah, that's a little confusing. So capital theta and lowercase theta. Lowercase theta is representing the model weights of the diffusion model, and then capital theta is representing the text embedding with a text encoder. So the text encoder is also a neural net, right? It's a function. And generally the text encoder and the image encoder are trained separately with just some generic pre-training task. CLIP is a very popular text encoder, and some VAE is usually the image encoder. In this work, we use stable diffusion, a specific instantiation of the latent diffusion model. The latent diffusion model consists of 3 main components: an image encoder that encodes a given image into a latent code, right? So that's where the latent here in latent diffusion model means it's basically that you're not performing this diffusion in the actual image space. So in this image, in this picture here, you see how we're removing noise, but it looks like we're removing noise from the actual image, right? But that's not actually what most diffusion models are doing. Most diffusion models are removing noise not from the image, but from the encoded image, right? Which is they're calling it the latent code. Okay, then a decoder that decodes the latent code back into an image. So you encode the image into a latent, you remove the noise iteratively, and then at the very end, once you have the final latent that has all the noise removed, then you turn it back into an image with the decoder. And the network that's actually doing the iterative denoising is usually a UNet, and is this model here, D. No. Okay. That's wrong. This needs to be green. Okay. So that's what a latent diffusion model is. So what is DreamBooth? So DreamBooth is a network fine-tuning strategy to adapt a given T2I denoising network d theta to generate images of a specific subject. So a latent diffusion model is an actual neural network, or really it's like a bunch of different neural networks. But DreamBooth is a fine-tuning strategy. So DreamBooth is a process. A latent diffusion model is more like a noun. It's more like a set of models that perform the actual generation. DreamBooth optimizes all the diffusion network weights theta. So when you're doing this fine-tuning strategy proposed in DreamBooth, what you're optimizing, what you're pushing gradients into, is the theta for the diffusion model here, the UNet denoising network. So DreamBooth is not going to be pushing gradients into the text embedding model. It's not going to be pushing gradients into the image embedding model or image encoder. It's not going to be pushing gradients into the image decoder. The only thing it's going to be pushing embeddings into is this theta, or pushing gradients into, sorry, is this theta, which is the parameters that compose this UNet denoising network. Given a few subject images, while also retaining the generalization ability of the original model with class-specific prior preservation loss. Class-specific prior preservation loss. So some loss that preserves the prior. Hey Hoopo, I've been watching creative builds. I've been watching for a bit now. I got my own image generation website, and I think they'll be integrating this paper soon. This is sick. The fact that they have a model generation LoRa's on the fly will let us create their own aesthetic LoRa's by uploading a few examples. I love it. Yeah, and I think it's good for a bunch of different reasons, because the way that you create LoRa's right now, you have to basically have the model training code running. Like you have to load that model on your system where you're going to be fine-tuning that LoRa. But if you have this type of hyper network instead, you can generate LoRa's without ever having the text-to-image diffusion model, right? So now you could have a service somewhere on some cloud, right, that the only thing it has loaded is this hyper network. And this hyper network is way smaller than this text-to-image diffusion model. So being able to separate these two things, I think, makes model inference and like any kind of startup that offers custom LoRa's, I think it's going to make it the actual services, at least in terms of like how many models you have to load and how does the inference work out. I think it's going to make it a lot cheaper too, because you'll be able to load this on a much smaller thing and serve it. Yeah. I like this very much. We saw this, a similar kind of hyper network in, I think, the Shape E paper. The Shape E. Yeah, this Shape E paper, which was pretty crazy, but they did something similar here where they had a neural network that generated MLPs for nerfs, which was fucking crazy. Yeah, here you go. So in this Shape E paper, which is basically a coming out of OpenAI, they have a network here, and the network outputs another network. In this case, it's the multi-layer perceptron, which is what a NERF is, right? A neural radiance field is basically a little neural network that'll tell you what the color of every single pixel is, given on where you're looking inside a volume. But this is the same kind of idea where you have a network that outputs a network, right? So this kind of network that outputs a network, I think we're starting to see it more and more, and it's such a great pattern because it basically, I think it has a bunch of different great things about it, but I love to see it. Okay, in the case of Stable Diffusion, this amounts to fine-tuning the entire denoising unit, which has over 1 gigabyte of parameters. It has way more than that. Stable Diffusion XL Stability AI Hugging Face. Yeah, so even just this, like, if I go to the Stable Diffusion XL, this is 13 gigabytes. So I don't know what the fuck they're talking about with this over 1 gigabyte of parameters. Like, this thing is 13 gigs. And I'm pretty sure most of it is a unit. Like, the 13 gigs includes other things, such as the VAE, and I think it also includes the image encoder. But I think the unit is way bigger than 1 gigabyte. So I don't know. 14 gigabytes is over 1 gigabyte. Okay, low rank adaptation. So that's a summary of what latent diffusion models are. Then we summarize what DreamBooth is, and now let's look at what LoRa is, a low rank adaptation. Low rank adaptation provides a memory efficient and faster technique for DreamBooth. So it's memory efficient in a couple different ways. It's memory efficient in the sense that your final LoRa weights, if you want to call them that, really they're residuals or delta W's, are actually quite small, and you can basically download them easily and load them easily. So they're memory efficient in that way, but it's also memory efficient in that you don't need to basically push gradients and into the full stable diffusion model, which means that you can it's also memory efficient when you're actually doing the fine-tuning. So it's memory efficient in the fact that just the final little LoRa checkpoint itself is small, but then it's also memory efficient in that you don't need to load the full model. LoRa proposes to fine-tune a network weight residuals. Residuals is basically just the difference between these weights at one point and then weights at a different point. It's just the residual is just a fancy way to say the difference between two things instead of the entire weights. That is, for a layer L in a weight matrix W, or a layer L with a weight matrix W, right? So you have some weight matrix W, which this d theta here, right? This diffusion model that is parameterized by theta, that theta includes a bunch of these weight matrices W and a bunch of layers. So those weight matrices W are going to have dimensionality n by m. N by m are just random numbers. It's going to depend on the model architecture. It's going to depend on the layer, depend on a bunch of different things, but all of those can have any value, right? The values of a weight in a neural net can have any value, negative infinity to infinity. Generally, they tend to be centered on 0 and tend to be basically somewhere between -1 and 1, because you have a bunch of normalizations and regularizations that kind of force them into that range. But technically, they can be. You could have a network. You could have a weight inside a neural net that was -9,732,000. You're pretty much never going to have that, but it's technically possible. LoRa proposes to fine-tune the residuals delta W, right? So some change delta W that you can apply to the actual weight matrix. So it's almost like, I keep saying this, but to me, I love thinking of LoRa's as a little bit of training in a bottle. It's like you're storing a little bit of extra training in a little bottle, and then you can use that bottle and apply that to the existing base model. For diffusion models, LoRa is usually applied to the cross and self-attention layers of the network. So the cross and self-attention layers of the network, what they're talking about there is that in a transformer neural net, transformer blocks have a couple different parts to it. They have these parts here, these feed forwards, which are generally multi-layer perceptrons, but the actual attention mechanism is happening here. And here you have self-attention, in which all the parts going into the attention mechanism are coming from this same part. So it's like paying attention to itself. And then here you have cross-attention, where it's paying attention to other things as well. So in this case, the encoder and the decoder. And in this paper, it was originally a translation paper, so it's basically 2 sentences in different languages. The cross-attention here would be between that. But generally, these attention layers are the ones that people apply the LoRa's to. A key aspect of the LoRa is the decomposition of the delta W matrix into low-rank matrix. So decomposition basically just means that you're breaking it down. You're breaking down this delta W matrix, which is going to be the same dimensionality as your weight matrix, right? N by M, but you're breaking it down into two smaller matrices, one that's N by R and then one that's R by M. And when you multiply these together, right, whenever you multiply matrices, you basically, the final dimensionality is the outside, right? So if you multiply A times B, the outside, which is N, and then M is going to be the final matrix, which is the same as this W, but the R dimension here is key because the R's need to match. So, but if you pick a small number for R here, right, which they say here, then a matrix that is N by R and a matrix that is R by M, both of these are going to be smaller than this W. So let's say N was 1,000 and M was 9,000. A 1,000 by 9,000 matrix is a whole lot more numbers than a 1,000 by 1 and a 1 by 9,000 matrix. So you see that by decomposing this delta W into these two matrices and picking a value of R or a rank that is very low, you can basically drastically reduce the amount of numbers that you need to use to define this delta W. All right, it's getting hairy in here. And then of course here delta W is just you're multiplying this A and this B matrix together. This decomposition. The key idea here is that rank is much smaller than N, and the combined number of weights in both A and B is much lower than the number of parameters in the original residual delta W. Yeah, and the less parameters you have, the more memory efficient and faster it's going to be to deal with that. Prior work shows that this low-rank residual fine-tuning is an effective technique that preserves several favorable properties of the original DreamBooth while also being memory efficient as well as fast. Remarkably, even when we set R equal to 1. Yeah, so I think we read the original LoRa paper, and it was surprising that even for an R of 1, it actually works quite well. Right? You would think that if you have a super low rank like this, you would just lose information and you would just get crap. But it actually does seem to work well. For Stable Diffusion 1.5, a LoRa DreamBooth with R equals 1 has approximately 386K parameters. So 386K total numbers, right, for this little delta W. And those are numbers, but then you need to basically store each of those numbers. And when you store them, you're going to store them at a specific, in a specific data type. There's different data types like floating point 32, floating point 16, and different data types take a different amount of memory, right? So 1.6 megabytes, right? A floating point 32 data type. Yeah, I just love the Wikipedia image here, right? Where basically this is a 32-bit data, and you can see that it takes 32 bits to store, right? Versus a floating point 16 takes 16 bits to store, right? So that's why the 386K parameters take 1.6 megabytes to store. All right, so those are the three basic components here, and let's get into the actual method. Our approach consists of three core elements, which we explain in this section. We begin by introducing the concept of lightweight DreamBooth to demonstrate how the low-rank decomposition of the weights can be further decomposed to effectively minimize the number of personalized weights within this model. Next, we discuss the hypernetwork training and the architecture of the model entails, which enables us to predict the LIDB weights from a single image. Finally, we present the concept of rank-relaxed fast fine-tuning. That should be interesting. A technique that enables us to significantly amplify the fidelity of the output subject within a few seconds. Figure 2 shows the overview of the hypernetwork training, followed by fast fine-tuning strategy in our HyperDreamBooth technique. Okay, so what do we got here? Figure 3, lightweight DreamBooth. We propose a new low-dimensional weight space for model personalization generated by a random orthogonal incomplete basis inside LoRa weight space. Oh, shit. They're LoRaing a LoRa. What? That's pretty tricky. Okay, so here, look at this. So kind of the key idea with the LoRa is breaking this delta W, right, which is N by M, and breaking it down or decomposing it into two things, A and B. And A is N by R, and B is R by M, right? And because this R is small, the total amount of weights that you need to store A and B is way less than the total amount of weights you would have needed to store this delta W. But then look at what they're doing. They're taking that a step further. They're saying, okay, well, normally you have A and B, which are N by R and R by M. We're going to do that again, and we're going to do N by A by R by B, and B by M. And you see this, the N by A and B by M is frozen. So they're almost like making a LoRa for the LoRa. So they get a LoRa that is kind of generic, and then they have an even smaller LoRa, because now, if we go back to the example that I was saying, let's say that N was 1,000 and M was 9,000. So you're taking your 1,000 by 9,000, and in the original LoRa, you're breaking it into a 1,000 by 1 and a 1 by 9,000, but now you're breaking it into a 1,000 by 100, and then what you're really storing is this 100 by 1 and this 1 by 50. It seems like this would make this bigger, but I think if you freeze this and you don't have to train this at all, then now you just effectively made an even smaller little LoRa. This achieves models of roughly 100 kilobytes in size, which is fucking crazy. 100 kilobytes compared to a LoRa of 1.6 megabytes. I mean, 1.6 megabytes is already very small. That's like less than the size of a song, you know? But 100 kilobytes is like a text file, which is absolutely tiny. 7.5% of a LoRa DreamBooth surprisingly is sufficient to achieve strong personalization results with solid editability. Damn. Yeah, 100 kilobytes, absolutely tiny. Creative builds. Could you not have a general LoRa model, then use a user LoRa model, and then say a face of that user LoRa model? Can this repeat an n number of times? Yeah, I feel like you could probably just keep doing this, right? You like, maybe that's where it goes. Ooh. Maybe eventually over time you have like chains of these kind of LoRas where you have like you're saying, you have one that is like faces, and then you have your specific one, but I don't know. Maybe you can do that. It sounds like a possible research direction if you're interested. Take this one step further, make an even smaller one. We present the concept of, lightweight DreamBooth. Given our objective of generating a personalized subset of weights directly using a hypernetwork, right? So they're using this hypernetwork to generate a neural network. I think what they're generating is this part here, which they're calling down AUX and up AUX. I think AUX probably stands for auxiliary. 1 kilobyte LoRa model inbound, 3-bit LoRa. 1-bit LoRa is just 0 or 1. It would be beneficial to reduce their number to a minimum while maintaining strong results for subject fidelity, editability, and style diversity. We propose a new low-dimensional weight space for model personalization, which allows for personalized diffusion models that are 10,000 times smaller than a DreamBooth and 10 times smaller than LoRa. Our final version has only 30K variables and takes up 120 kilobytes of storage space. The core idea behind Lightweight DreamBooth is to further decompose, so basically just take it one step further, the weight space of a rank 1 LoRa residual. Specifically, we do this using a random orthogonal incomplete basis within the rank 1 LoRa weight space. So they're finding a set of, or a basis, which is basically, right, this idea of, think of this as the LoRa, right? Let's think of the LoRa as this vector, and you're finding this basis within that, which means that there's a simpler pattern inside that LoRa. Which is pretty crazy anyways, right? It's like, how are you finding an even simpler or lower rank kind of thing within an already rank 1 LoRa? Like, what? It's fucking crazy. The approach can also be understood as further decomposing the down and up matrices of LoRa into two matrices, A auxiliary A train and B auxiliary A train. So it's basically just further decomposing. So now you have four of these bad boys, where the aux layers are randomly initialized with row-wise orthogonal vectors and are frozen, and the train layers are learned. Two new hyperparameters are introduced, A and B, which we set experimentally. Yeah, so the same way that in the LoRa paper, this R, you have to pick a value for that. In the LoRa paper, they try a couple different values, right? This R is a hyperparameter, which means that you don't know what the best value is. You have to try a couple different ones and see which one works best. They tried, I think, 1, 2, 3, all the way to 8, and it turned out that 1 is actually the best one, which turns out great because it's the smallest one. But when you're doing that again, now you're going to have to pick these numbers. You're going to have to pick a number for A and a number for B. And the number that they picked is 150, which they set experimentally, which basically just means they tried a bunch of different ones and then they picked the one that worked the best. And thus, delta Wx, right, the residual of the weight matrices for the attention layers is going to be these four matrices here. R is much smaller than n by n, and A is smaller than n, and B is smaller than m. So all of these numbers are smaller than each other. A aux and B aux are randomly initialized with orthogonal row vectors with a constant magnitude and frozen. And B train and A train are learnable. Surprisingly, we find that A and B 150 yield more than which yield models that have roughly 30k trainable variables and 120 kilobytes in size. Personalization results are strong and maintain subject fidelity. Okay. So here's your hypernetwork. So your hypernetwork is actually composed of a couple different pieces here. So hypernetwork consists of a visual transformer encoder. So much like in a latent diffusion model, you're encoding the image. So you're taking these images here and you're encoding them into some kind of latent. You probably are using the same encoder that you use in your diffusion model, right? Just for simplicity's sake, you wouldn't want to use two different vision encoders. Probably just use the same one. Translates face images into latent face features that are then concatenated into latent layer weight features that are initialized by zeros. So these are the different parts of the LoRa. Where are these weights coming from that are initialized? A transformer decoder receives the sequence of the concatenated features and predicts the values of weight features in an iterative manner by refining the initial weights with delta predictions. Ruh-roh. This hypernetwork is not just a one step. It's not just one inference step. You see how they have k iterations here? It's like an iterative process where the output of this is a bunch is not actually weight values. It's weight features. So it's some kind of latent or vector or embedding that represents the values of those weights, and that is going here and coming back in. So you're basically iteratively getting features that represent those weights, and then this little linear layer here actually turns it into delta layer 1 weights. So here, these aren't actually weights, these are weight features, and then here, these are weights. It's fucking crazy. You can have features that represent neural network weights. The final layer weight deltas will be added to the diffusion network and are obtained by passing the decoder outputs through a learnable linear layers. Hypernetwork for fast personalization of text-image models. We propose a hypernetwork for fast personalization of pre-trained text-image models. Let theta tilde denote the set of all LIDB residual matrices, A train and B train, for each of the cross-attention and self-attention layers of the T2I model. In essence, the hypernetwork Ada, I think this is Ada, right? Ada Greek letter. Yeah. Kind of a weird, It's called Ada, but the capital version of it is H, and then the lowercase version of it looks like an N. So super confusing, but this is the Greek letter Ada. And here they're basically saying you have a hypernetwork function H, and this hypernetwork H is parameterized with Ada. Takes the given image X as input, so you have some image X, and predicts the LIDB low rank residuals. I feel like it would have been less confusing if they just took this this vision encoder here and put it outside, right? Much like whenever here they defined the latent diffusion model. The latent diffusion model takes the image and turns it into a latent code, and then does all of that in the latent code. But the image encoder isn't really considered part of the denoiser network. Here, the way that they're writing this, the encoder is part of the hypernetwork, but I feel like I would have just taken that out just to be a little bit less confusing, right? Have the image encoder be separate. But ultimately, your hypernetwork H of N takes this image and then outputs this theta hat here, which are the low rank residuals. The hypernetwork is trained on a dataset of domain-specific images with vanilla diffusion denoising loss and a weight space loss. So the vanilla diffusion denoising loss is this here, right? So you can see here, this is an L2 loss, right? You see these parallel bars here. This, and with the 2, that means it's an L2 loss. It's the difference between two things squared. And what are those two things? Well, one of the things is the image here, X, and then the other thing is what's coming out of the latent diffusion model, right? So the latent diffusion model produces images given some input image, noise, and then the context vector C. So C is going to be your text. This alpha here is going to be a hyperparameter. So anytime you have a loss that is composed of multiple losses, you're going to have to pick hyperparameters that tell you how much more important is this loss than this loss. And then this weight space loss here is just the difference between these weights. So theta, which is the original denoiser weights, minus theta hat, which is the new denoiser weights, which come out of this hypernetwork here. And I almost wouldn't call this a loss. I would almost call this a regularization term. Really what you're penalizing here is the weights from drifting too far away from the original weights, right? You don't want the weights to drastically change the denoising diffusion model, because if you drastically change it, you're going to lose all the good stuff that was already there, right? What they're calling the prior, which is basically all the effort that you put into pre-training this diffusion model. If the difference between the new weights and the old weights are too big, you're basically losing that. So I wouldn't call this a weight space loss. I would call this just a regularization term in the weight space. Weight regularization. X is the reference image. Theta is the pre-optimized weight parameters of the personalized model for input image X. D theta is the diffusion model, conditioned on the noisy image X plus epsilon. And it's actually not, this isn't actually correct either. You're not adding the noise to the image. You're converting the image into a latent and then adding the noise to the latent. Supervisory text prompt C, and finally alpha and beta are hyperparameters that control for the relative weight of each loss. All right, and then here when it says weight underscore 1, weight underscore n, these are basically the delta W's for each layer, right? So your actual diffusion model is going to contain transformer blocks at different layers, right? This UNet is going to have basically cross-attention and attention mechanisms at each of the different layers, and you're going to be training a little delta W for each one of those layers, and that's what the fact that there's multiple of these weights here. Supervisory text prompt. We propose to eschew. I think I know what this word means, but I don't actually know what this word means. Eschew. Deliberately avoid, abstain from. I bet you they felt fancy when they typed that word in. Any type of learn token embedding from this task. and our hypernetwork acts solely to predict LIDB weights of the diffusion model. We simply propose to condition the learning process a V-face for all samples where V is a rare identifier described in 25. So rare identifier is just a fancy way of saying that when you're trying to teach this diffusion model a new concept such as your face, you don't want V to be something like dog, right? Because then every time you're pushing a gradient in there, you're basically overwriting the information of dog. You're confusing the diffusion model because it already has an idea of what a dog is. So you're kind of telling it, no, this is a dog, and then it starts to get confused. It'll start to lose that nice little prior that it's built over all its pre-training. So by having this rare token, right, a token that it's never seen before, now it becomes much easier to basically introduce this new concept into the diffusion model without overwriting or forgetting any of the previous concepts that it's learned. At inference time, variations of this prompt can be used to insert semantic modifications. For example, a V-face in impressionist style. Okay, hypernetwork architecture. Concretely, as illustrated in Figure 4, we separate the hypernetwork into two parts, a VIT image encoder and a transformer decoder. We use a VITH for the encoder architecture and a 2 hidden layer transformer decoder for the decoder architecture. Is this VITH frozen? Oh shit, that might be an issue. Okay, so I was saying, why don't they just pull this VITH out of here, right? This vision encoder out of here, just so make it a little bit cleaner. But I think the reason they might leave it in here is because they actually push gradients into it. That's kind of crazy if they do. The transformer decoder is a strong fit for this type of weight prediction task since the output of a diffusion, UNet, or text encoder is sequentially dependent on the weights of the layers. In order to personalize the model, there is interdependence of the weights from different layers. Yeah, I guess I agree with that, right? It's like in the UNet, right, these little delta W's, they're not going to be independent of each other. You want those little delta W's to be aware of what the other delta W's are. That makes sense. This dependency is not rigorously modeled in the hypernetwork, whereas with a transformer decoder with positional embeddings, this positional dependency is modeled, similar to the dependencies between words in a language model transformer. So in a transformer decoder, and in the encoder as well, but you have positional encodings, and these positional encodings are basically added to the sequence, and they allow this attention mechanism to understand where those different parts of the, for example, it could be a sentence, or in the case of a vision coder in an image, the positional encoding tells you where is that little chunk that I'm giving you here. What does that represent in a sentence? Is it the beginning of the sentence, the middle of the sentence, or the end of the sentence? And in the case of an image, is it the first? Is it the top left of the image, or the bottom right of the image, and so on? So here, what the positional embeddings are representing is where along this UNet layers, where along all the different layers in this UNet is this particular little delta W. To the best of our knowledge, this is the first use of a transformer decoder for a hypernetwork. Is that... Overview of our encoder. Yeah, so I think the kind of hypernetwork that they have here in this shape E is just an encoder, so it's not a decoder. Each vector is a sequence passed through a latent bottleneck, projection layer, output tree to a single row. Encoder architect. Okay, yeah, so maybe they're correct. I don't know enough to know a different instance of a hypernetwork that uses a transformer decoder. Iterative prediction. We find that the hypernetwork achieves better and more confident predictions given an iterative learning and prediction scenario. It refines its own output. Intermediate weight predictions are fed into the hypernetwork, and then the network's task is to improve that initial prediction. We only perform the image encoding once, and these extracted features F are used for all rounds of iterative prediction for the hypernetwork decoding transformer T. So the iterative nature here is just to basically keep running this decoder with the updated weight features. And these aren't even delta W's. These are features or vectors that represent the delta W's, right? So what they're saying, though, is that this VITH here, you only run it once. So once you get this face, they're calling it a face, but it's basically just an image vector or an image embedding, that gets the same one gets fed every time. So you're not iteratively updating this face embedding. What you're updating is these weight embeddings. This speeds up the training and inference, and we find that it does not affect the quality, specifically the forward pass of tau, or T, which is the hypernetwork. T is not the hypernetwork. What is T? The transformer in the hypernetwork. Okay, so T is the transformer in the hypernetwork. And T takes F, which is the image encoding, or the face embedding, which is what they're calling it here, and then theta k minus 1, where k is the total amount of iteration steps. Terminates when k equals s. S is a hyperparameter. Okay, so they're because they have to do a bunch of steps, now they have to introduce another hyperparameter, which is how many of these iterations are you doing. So similar to how a diffusion model, there's a hyperparameter here, which is this t, right? How many steps of denoising are you doing? There's going to be a similar kind of thing here where there's a hyperparameter k, which is how many steps of this weights are you doing here. And actually, the second those words came out of my mouth, I was like, what if instead of a decoder here, transformer decoder, they have a diffusion model, right? Wouldn't this be better done with a diffusion model? Get rid of this weight feature here and this linear thing that turns this weight feature into an actual delta W, and get rid of this transformer decoder. Turn this entire brick here into a diffusion model with k steps. That's pretty cool. Somebody needs to do that. So you get one single image embedding and then use that to train the hypernetwork. Is that the average of all the input images, or you do that per each image? You do that per image. So you're going to do that for a bunch of images. And I think they mentioned the data set. I feel like I vaguely recall this. This is the generic part, right? So they're doing it with a bunch of different images in a similar domain. We literally just read this. It's like somewhere written here, but they'll tell us what the data set is. They're doing this per image. Weights theta are initialized to 0 for k equals 0. Trainable linear layers are used to convert the decoder outputs into final layer weights. We use the Celeb A HQ, so this is the actual data set they're using. Celeb A HQ, which I think is basically just pictures of celebrities. HQ means high quality. This is a very popular data set. This was really popular back in the GAN days, back when people were training GANs and generating faces. They would use this celebrity data set for training the hypernetwork, and we find that we only need 15K identities to achieve strong results. So the hypernetwork is trained on 15,000 celebrities, right? And it's learning. What is the hypernetwork learning? The hypernetwork is learning, given a bunch of pictures of a celebrity, it's learning how to basically create these delta W's that adjust a diffusion model such that it can generate pictures of that celebrity, right? And you train that on 15,000 celebrities, and then you freeze that hypernetwork, and then now you can use this hypernetwork, give it a picture of your face, and it'll say, okay, well, here's your face, here's the delta W or the LoRa that you can use to modify this diffusion model to generate pictures of your face. So there you go. This is just such a clever idea, you know, I just love this. Rank relaxed fast fine-tuning. We find that the initial hypernetwork prediction is in great measure directionally correct and generate faces with similar semantic attributes as the target face. Nevertheless, fine details are not sufficiently captured. We propose a final fast fine-tuning step in order to capture such details, which is magnitudes faster than DreamBooth, but achieves virtually identical results. Specifically, we first predict personalized diffusion model weights with the hypernetwork. and then subsequently fine-tune the weights using the diffusion denoising loss. Okay, so basically what the fuck is going on here is that they try, ideally you could tell that what they really wanted is for this hypernetwork to produce these delta W's, and then those delta W's would just work out of the box, but unfortunately they don't. So they're going to take those delta W's, right, which are the LoRa's, and they're going to fine-tune them a little bit. So you can feel that what they really wanted is for just this first step to basically work, right? And then you wouldn't have to do this fast fine-tuning, right? It would have been amazing if you could just feed a picture, get into the hypernetwork, get the LoRa, and the LoRa just works out of the box. But unfortunately, it doesn't work great, so they have this additional process where you fine-tune it a little bit, and you basically do this standard reconstruction loss here to say, hey, this picture should actually be this picture. And it'll tune those LoRa's a little bit. Okay. And then subsequently fine-tune the weights using a diffusion denoising loss, right? So basically the same loss that we saw before, where you're basically taking the difference between these two images and doing an L2 loss there. The key contribution of our work is the idea of rank relaxed fine-tuning, where we relax the rank of the LoRa model from R equals 1 to R greater than 1 before fast fine-tuning. That's not great. Why do they have to do that? Specifically, we add the predicted hypernetwork weights to the overall weights of the model and then perform LoRa fine-tuning with a new rank. Ooh, the fact that it doesn't work at rank 1 is kind of sketch. This expands the capability of our method at approximating high-frequency details of the subject. High-frequency details means that it's like the texture is incorrect, right? So low-frequency details would be like the position of the eyes relative to the nose, relative to the face, right? Low frequency, think big. So, never mind. Low frequency, think like a sine and cosine wave that's like very stretched out, right? The frequency is low. High frequency, think about like a sine or a cosine that's very high frequency, right? Up and down very, very fast in a very short amount of time. So high frequency details refer to things like texture and the edges and colors and stuff like that. Usually the lower things in a convnet. Low frequency details are more high level semantic things like the eyes, the composition of the image, and so on. So basically they're letting you know that the reason they had to do this rank relaxed fine tuning is because the output was kind of weird looking in the high frequency, so that something's off with the texture, the hair, maybe the color of the skins, things like that. Giving higher subject fidelity the methods that are locked to lower ranks of weight updates. We are the first to propose such rank-relaxed LoRa models. I don't think this is a flex. I feel like this is a negative, right? I feel like it would have, if it just worked at R equals 1, that would have been much better, but the fact that you had to relax this, that's a negative thing to me. So I don't know if that's something you want to be bragging about. We use the same supervision text prompt, a vPhase, for this fast fine-tuning. We find that given the hypernetwork initialization, fast fine-tuning can be done in 40 iterations, which is 25 times faster than DreamBooth or LoRa DreamBooth. So the second part of this takes 40 iterations. So training the hypernetwork, you do it with the Celeb A dataset, 15,000 different faces, 15,000 unique faces, but I bet you that the total amount of training steps is actually much larger than this. There's probably many training steps per identity. But then fine-tuning the LoRa that comes out of that hypernetwork, you can do in 40 iterations, which is way faster. Okay, we implement our HyperDreamBooth on Stable Diffusion v1.5, and we predict the LoRa weights for all cross and self-attention layers of the diffusion unit, as well as the clip text encoder. For privacy reasons, all images used for visual are synthetic from the SFHQ dataset, synthetic face high-quality dataset. For training, we use 15K images from the Celeb A HQ. Okay, so I take it back. I thought that this was the picture of one of these researchers, but it's not. This is just some random synthetic face. So this is like a "this person does not exist" face. Okay. Input image. They have the same face in different styles. I mean, these all look fine. They look a little weird. No, there's just something unsettling. I don't know what it is. Our method can generate novel, artistic, and stylized results. Instagram, Pixar character, face with bark skin, face as a rock star, professional shot. Given the static nature of hypernetwork predictions, some samples that are out of distribution, OOD, for the hypernetwork due to lighting pose can yield suboptimal results. Yeah, this is the problem, is that this hypernetwork is only good for celebrity faces, which we recognized immediately, right? So as soon as we looked at this, we looked at this paper, I was like, this is a little sketch, right? The fact that every single one of these pictures is 90% of it is face, and it's just right centered right in the middle, right? And I was like, that generally is not indicative of something that can generalize outside of that distribution, right? There's a distribution of face images that this hypernetwork has been trained on, right? The Celeb A dataset is a very, very narrow dataset. It's basically just pictures of faces that are centered. So that's kind of what they're saying here, is that unfortunately, if you try to feed this a picture that is not a face that is centered, it's going to be out of distribution and it's not going to yield good results. Specifically, we identify 3 types of errors that can occur. This is a typo here. It should be identify 3 types of errors that can occur. There can be 1, a semantic direction error in hypernetwork's initial prediction, which can yield erroneous semantic information of a subject. Incorrect subject detail capture that yields samples that are close to the reference identity but are not similar enough, or underfitting of both hypernetworks and fast fine-tuning, which can yield low editability. Yeah, so here they're trying to do a little bit more outside of the distribution, right? So graffiti of the person, it's going to be a little bit more difficult, right? And you can tell that right here it just instantly fails. And here, this is, I forget what these are. These are like little Funko Pops, right? I think that's what they're called, but they're basically little toys. These actually are quite good, but you can see that they're the ones that are kind of a big face centered actually perform better than the ones that are like inside the box. Compare randomly generated samples. We observed that our method generally achieves very strong editability, surpassing competitive methods. HyperDreamBooth, textual inversion, DreamBooth, HyperDreamBooth, textual inversion, DreamBooth. Yeah, it kind of seems like this is the best. But these are cherry-picked, of course, so you got to take it with a grain of salt. Comparisons. We compare our method for face, subject fidelity, and prompt fidelity. So what they're doing here is they're taking these images and feeding them into different image encoders. So Dino is an image encoder. Clip I is another image encoder. Clip T is a text encoder, actually. And then here you have face rec, which is some kind of face score. And what they want is higher is better here. This up arrow means that the higher the score is, the better. And they're basically showing you that their technique, HyperDreamBooth, is able to get a face that looks more like the original face. We increase the number of iterations to 1,200 in order to achieve improved personalization. Results are shown in Figure 7. Our method outperforms textual inversion in DreamBooth. Good to know. We compare our method to textual inversion in DreamBooth using a face recognition metric, FaceRec, which uses an inception ResNet trained on VGG Face 2. So this is an ancient network. An inception ResNet, that's like a 2017, older than that, 2015? It's got to be ancient at this point. We use 100 identities from Celebrity AHQ, 30 prompts. We show that our approach obtains the highest scores for all the metrics. One thing to note is that face recognition metrics are relatively weak in the specific scenario, given that face recognition networks are only trained on real images and are not trained to recognize the same person in different styles. Yeah, I agree with that. Any kind of image distance metric is IMO pretty weak. Differently tuned hyperparameters to close the optimization time gap. Find that increasing the learning rate and decreasing the number of iterations, there is a degradation of results. So the learning rate is how big each step you take in your gradient descent process is, and then the number of iterations is how many steps you take. That's one way to think about it. So you can take less big steps, or you can take a lot of smaller steps. Generally, you want to take smaller steps and more of them than big steps. The only negative is that it can take forever to get to where you want. So here they're kind of tuning. You can see that there isn't much of a difference, especially because these metrics are kind of bogus anyway. So I don't know what 0.1 difference in dyno score necessarily means. HyperNetwork. We ablate several components, including not using the HyperNetwork component at test time, only using the HyperNetwork prediction without fast fine-tuning, and using our full method without iterative prediction. So this is the more interesting stuff here, right? They talked about how in an ideal world, they would have wanted the HyperNetwork to produce the delta W, the LoRa, and then that's it. And you don't have to do this secondary fast fine-tuning step, right, where they gradually relax the rank of the LoRa. That would have been great. And actually, it seems like they should have just kept that, right? Because, for example, only Hyper versus this one here, like, that's not too far off. It feels like it's kind of close enough that maybe they should have just left it like that and gotten rid of this relaxed rank fast fine-tuning. Conduct a user study. This is what I want to hear. That's the best way to judge the quality of these generative image models. We increase the learning rate, tune the weight decay to compensate for the change in the number of iterations. Note that HyperDreamBooth is roughly equivalent to only doing fast fine-tuning without the HyperNetwork component of our work. We show an ablation study. We remove the HyperNetwork, only use the HyperNetwork without fine-tuning, and use our full setup with iterative HyperNetwork predictions. We show results in Table 3, and our full setup with iterative prediction achieves the best subject fidelity. User study for face identity prediction. Face identity preservation. That is actually... Humans are so good at recognizing faces that I feel like a user study for face identity preservation is orders of magnitude better than whatever this face rec score is here. Ask the user to rate which one has the most similar face identity. We test a total of 25 identities and so on. Damn, they blow this out of the water. You see, look at that. Compared to this is the user study, so this is the score that actually matters, right? This is having people look at pictures and then say which picture looks most like the original human, and it's not even close, right? Like 0.64 versus 0.23. Like, look how much better, how much bigger the magnitude of the difference is here compared to here, right? No, actually, what we should be comparing to is here. Yeah, look at this. This face rec score is like virtually identical for all of these. Versus if you go to the user study, huge difference. Societal impacts. Our proposed method inherits many possible concerns. Reproducing unfair biases. Presented in a litany of recently personalization, blah, blah. Future research in generative modeling and model personalization must continue investigating and revalidating these concerns. I don't know. Do they? Like, does it matter? Do you need to be constantly kind of pretending that this is actually going to cause a huge amount of harm? I don't think it's going to cause a huge amount of harm. I don't think there's like any way in which generating images is going to cause harm. Right? Like, I don't know, like, should we ban horror movies because people get scared about horror movies? Like, I just don't agree with this. Like, to me, there's no image that you can create that is going to harm someone. In this work, we have presented HyperDreamBooth, a novel method for fast and lightweight subject-driven personalization of text-image diffusion models. Our method leverages a hypernetwork to generate lightweight DreamBooth parameters for a diffusion model with subsequent fast, rank-relaxed fine-tuning that achieves a significant reduction in size and speed compared to DreamBooth and other optimization-based personalization work. Say that fast 10 times. We have demonstrated that our method can produce high-quality and diverse faces with different semantic modifications while preserving subject details and model integrity. Agreed. Okay, let's see if there's no appendices. But, I don't know, that was a pretty good little paper. Let's summarize this paper. Let me take a big sip. Let's summarize this, and let's go. Ugh. Okay. So, today, we read Personal HyperDreamBooth, Hypernetworks for Fast Personalization of Text-to-Image Models. This is a paper published in the 13th July of 2023, coming out of a Google research. This is yet another fine-tuning paper where you are fine-tuning a latent diffusion model, which removes noise from a latent image such that you can generate an image conditioned on text. These are known as text-to-image models. This approach works on any text-to-image model, so Stable Diffusion, HyperDreamBooth, or not DreamBooth, ImageGen, whatever they're using inside Midjourney, right? All of these different latent diffusion models are basically using the same strategy, so any of these fine-tuning techniques will work on them. I kind of got brain farted there. Okay, the main contributions of this paper are basically this idea of taking LoRa one step further. So low rank adaptation is a very popular fine-tuning approach, and the secret sauce with LoRa is that you can decompose a delta W, right, or a weight residual, which allows you to adapt the weights of a pre-trained diffusion model without messing with the original weights of the pre-trained diffusion model, by having this delta W and decomposing that into two matrices, which have a much lower amount of numbers, which means that it's faster and more memory efficient. In this paper, they're taking that one step further and basically decomposing the two LoRa matrices into four matrices here, which they're calling the aux and train. So that's kind of one idea that they introduce. Another idea that they introduce in this paper is this idea of a hypernetwork. A hypernetwork is a network that generates a network, right? So it's a neural net that generates neural nets. But in this case, it's not actually generating a neural net. What it's generating is these delta Ws, and these delta Ws are weight residuals, which are basically LoRa's, which are just a matrix of numbers. This hypernetwork, let's go to the actual image of that. The hypernetwork, what it's doing is it's taking a bunch of images from the celebrity data set, encoding them into a image vector or an image embedding, then feeding that image embedding into this transformer decoder, which iteratively figures out these weight features, and those weight features are then decoded into actual delta Ws for each of the different layers of the UNet part of a latent diffusion model, specifically the attention mechanisms in the UNet. So the part of the UNet that is basically looking at the context, which is the text, and modifying the ultimately removing the noise. The losses they use here are pretty simple. They're using basically this L2 loss between an image space, and then they're using a kind of a weight regularization where they make sure that the weights don't change too much. So that's the basic process. One thing that I didn't like is that if it would have just been this phase 1, that would have been amazing. But then they have this phase 2, or actually, then they have this phase 2 where unfortunately, they can't just feed a picture of you into this hyper network and get a LoRa that works. What they end up doing is they feed a picture of you into this hyper network, get a LoRa, and then do a couple more fine-tuning steps on that specific LoRa in order to get a LoRa that works better. So I feel like they tried to not have to do this, but they ended up having to do this. Anything else? I don't know. I just thought this was a well-written paper. I loved the introduction and I loved their breakdown of the preliminaries. Very good preliminary section here because it's short and sweet. You know, a lot of preliminaries kind of get carried away and they spend half a page talking about something, but here they kind of give you a short and sweet representation. I think this is powerful. I like this idea of using hyper networks to generate LoRa's. I feel like there's something to do there. One interesting thing I thought about here is perhaps getting rid of this decoder here and making this a diffusion model itself, making the hyper network a diffusion model in weight space. That would be pretty badass. But yeah, what else? Maybe one thing I didn't like is that they trained this hyper network on a Celebrity A HQ dataset. The Celebrity A HQ dataset is a very narrow dataset. It's pretty much only pictures of faces that are centered and basically cropped in a specific way. So this this hyper network is only going to work for pictures of faces that are like that, right? If you try to do some out of distribution image, like a picture of you in a motorcycle jumping, it's not going to work, right? Because the relative size of your face and the positioning of your face is going to be out of distribution compared to what this hyper network has been trained on, which is the Celeb QA. But I don't know, pretty cool little paper, pretty cool results, and I can't wait to see what people do with this and how they apply it. That's basically it. Thank you, Creative Builds. Thank you, Erland. Thank you, QD. Thank you, Cosmos and Nadi, for the questions and comments. Yeah, see you guys on Wednesday. Wednesday, I have a stream. We're going to be doing some coding and hanging out. But have a great Monday. Do something interesting. And see you guys later.